Hi everyone, my name is VV and my registration number is 17BEC 0310. Due to the current corona pandemic situation, I have done my internship in Coursera and my topic is VLSI CAD, which means very large scale integration design in computer aided design. Now I am going to show how I learned this VLSI CAD. Nowadays it is very important to design VLSI CAD. In computer aided design device, we are going to design how these transistors and chips are connected, and main theme of this C CAD is VLSI CAD is converting a complex situation to a very smaller blocks, and the entire process is known as CAD, which we will design. And coming to the topic, there are many theorems and some of the important topics by which we will use that and use it in VLSI CAD. Coming and to the first topics, its name is Shannon's theorem. The Shannon's theorem definition is this is the main function f of x1, x2 and so on xn is equal to x1 into f of 1 comma x2 and so on xn plus x1 bar into f of 0 x2 x and so on. This f of function f of x1, x2 and so on xn is divided into two parts, which is a positive cofactor and it is a negative cofactor. In the positive cofactor, we will take xi as equals to 1, and in negative cofactor xi is equals to 0. By splitting like these two factors, the complex problem is reduced in simpler ways. So coming into the mux, as we already know, where we will use this Shannon expression, and we will be taking a function and the inputs may be 0 or 1. It is a 2 by 1 mux and the select line is x when it is 0 and when it is 1. When the select line is 0, then it will the output input as 0 will be taken, and when the select line is 1 and the input 1 will be taken, and when the 0 is taken, the negative cofactor will be coming, and when 1 will be taken and the other cofactor will be coming. As we know, the output of this mux is x bar into this, if we take as input a, x bar into a plus x into this one as b plus b. Like this we will be taking in the mux there, where we will be using Shannon expression and simplifying it in a very easy manner. And there are some of linear properties of cofactors, where if f is equals to h bar, and then if we take fx, then it is equals to f hx bar. And now I have given these linear properties, and though by going through it we can learn easily. And as we know, Boolean derivative, and as we have seen in max, everywhere derivative and how to find it. And now here in the Boolean expressions we can find the difference in the expression, like by with the help of dou f by dou x. The Boolean difference or Boolean derivative of the function f with respect to the literal x is defined as dou f by dou x equals to fx NOR gate with fx bar. And if we take as an example here, it is a big function logic, and the inputs are a, b, c and so on, w and x, and the output of f of it is a function of a, b, c and so on, w come x. When the output is 1, it means, and now here it is explaining, when we are taking abc as any value and we are getting as 1, whenever if we change the value of x, the output value also gets changed. This will they So this is been explaining in this concept. And coming to the there are two quantification operators. They are universal quantification, where for every value of f, that is equals to fx into fx bar, and external quantification, it is there exists f is equals to fx plus fx bar for multiple variables. This AND gate will be and for AND gate this expression will be used, and for OR gate for this will be used, because in AND gate for every value it should satisfy. If both a and b are 1, then the output we will be getting 1. If any one is 1 and the other is 0, we will not getting the output as 1. So for every value of x and y we will be taking this expression, and for there exists any value of x and y, this expression will be used for OR gate. And coming to the network repair, like that we deeply will be going here. Let us take a specified example and a got example. This is the function ab plus b bar, and the inputs are a and b, and the output of this function is f of a and b. And we have to we have to design a function which will be suitable, so that the output gab will be 1. So we will be going through a simple example, and now I am taking the very good known logic. uh, Here we will be taking a NOT gate and AND gate, and now I am giving a OR gate. This function f of a and b. Now, as we know, now I am keeping here 4 by 2 mux. In this mux, we should know d0, d1, d2, d3, and the input of this mux is a and b. And this example I have kept here, and this I have well known example I have given here. And the what should be have to keep this question mark. We have to think that I think, according to my knowledge, we have to keep there an XNOR gate, because the when the here for every value of a and b we should get the output. If we want to, if we get the value, we have to repair it, and so that we should get the correct value. To get the correct value, here we are keeping Hmm. For XNOR gate, if both the inputs are same, then we will get in the same output as 1. So both should be 1. As f of a and b, and if both are 1, then we will be getting the 1. In this expression, we have to see now. Here I have given that for all a b of z of d naught d1 is equals to 1. As this function, in the question they will be given, and this should be equalized to 1, and we should substitute values of d0, d1, d2, d3 by substituting the values, and we will, for a particular value, we will be getting the output as 1. So keep on substituting, for which value it will be getting 1, we should substitute that values in this mux d0, d1, d2. This mux is fixed, so we should not change these values anymore. So total function is dependent on a and b for every values of z. So we have got that the final conclusion for every values of z. By knowing the values of d0, d1, d2, d3, we will be not changing this anymore. So ab is the value we are for every value of a and b. You will be getting the output. Like this, we can repair a network. And coming to the boolean function using a cube. If a cube is given and we have to get a boolean function, this is one of the important or interesting concept, where we will get the output boolean as like this. Now let us take a cube. As all of you know, let us take this axis, x axis as a and y axis as c and z axis as b. At this point both are in 0, and in this axis b is moved forward, so that we will be taking 0 1 0, and this axis z axis is moving forward, so we will be 0 0 1. Like this, every axis we will represent. And we are now in the question they have given circles in these positions. Now let us take a this part, this 0 0 1 and 0 1 1 and 0 1 0 and 0 0 0. In this part, every b and c is changing. Look at in this, here b is changing, here c and c, except a value is not changing. So as here a value is 0, we will be taking as a bar. We have to combine all these 6 parts in a one way, and we have to get the boolean function. Like this one, now here we have got this, and if we take this, we will be getting another, like that. And if we take this part, we will be getting another. By taking all this and applying like as OPR POS, and we will get the final expression as a bar plus bc plus ab. This is one of the important quite interesting topic. The above which I have explained, they have given like this. Not a means 1 0 will be putting as it is a negative, and remaining bc is there, so we'll be giving 1 1 1. This position of the notation which they have given in a clear manner, which we can explain it. And yeah, and unit is one of the concept where we'll be using unit. Let us take a SOP operation of example, AB plus AC plus. What is unit? We have to know it. let us see here. A is here and A is here. Both the expressions are same. Both are same. One is A and other is A not, but not like that. Both are A and A, and B is there, same, and another B is not there. Leave it. C bar is there and another C bar is there. D is there and another D is there. So every expression is repeating same, and with respect to another one is same, and they are not different. So this is an unit. Coming to here, it is x and here is x bar. We can conclude that this is not a unit. So function example a1 is unit and this is not an unit function. And here we have given positive unit and next negative unit. If the function is changing to 0 to 1, then it is a positive unit. 1 to 0, then it is a negative unit. And binary decision diagram, which we call as BDD, it is very important and one of the concept. If let us take a truth table, and this dotted line represents 0, it carries 0, and a straight line, this full-fledged line gives and carries 1 as the input. Let us take here, this carries 0 and this 0 and this 0, 0 0 0, and the function is 0. And let us take like this 0 1, not like 0 0 1, this expression like that. F for a something given function f, we will be taking substituting that value and we will getting the f value. By decision diagram we will get the final output value. This is one of the method in used in CAD. Okay, now BDD rules, some of the rules, as I have said, dotted line indicates 0 and a straight full-fledged line indicates 1. Now this, when you come to here, x2 and x2 are the same and in the same level. They both are isotropic nodes, so we can merge them and eliminate redundant tests. When you see here from this picture, you will be getting like this: x2 x2 are same, and x3 x3 x3, and 0 0 1 0, and by from this we have to get a canonical form finally. When canonical form is the most reduced form of SOP or POS, so the expression is relevant and it is easy to understand. By using these merging concepts and everything, we finally will be getting x1 x2 x3 0 1, and this is the final output. As I already told you, XNOR will be taken here. So by fixing the D0, D1, D2, 3, for every values of A and B, we will be getting this output. SAT. SAT is very important. We will be learning in the next session. Like this, the satisfactorability. Satisfactorability means for what values of x1, x2, and the function output is 1. What we have to do, which values we have to keep so that it will be satisfying, or not any, or we are not able to find any solution. We have to know that. SAT will be telling that everything. SAT we have complete standard SAT, standard form CNF, and conjugate to normal form, which is POS. We can call it as standard POS form. Let us take an example: a plus b into, which is a POS form, and every product is called as class. This is a class, this is a class, this is a class. As it is a bar, it is a negative literal, this is a positive literal. If bar it is there, it is 0 indicated, and if it is a positive, it will be indicated as 1. We will be coming to know in the next slide. And if we take an example like y is equals to x plus y plus z into x bar plus y into y bar plus z into x bar plus y bar plus z bar. Now we have to keep on substituting recursively, like now let's take x is equals to 1 and x equals to 2. When we take x is equals to 1, what are the possible output? X equal to 0, what is the possible? For this value, y values, for these values and z, and like that we will be keep on substituting values. For what value of x, y, z we will be getting y is equals to 1, that value satisfies the given function. So for that particular value, we can say that SAT is equals to 1. For some particular value, we will be getting that value. So this process we have explained here: decision and deduction, how to find yes or no, like that I will be knowing that. For one is a is equals to 1, b is equals to 1, substitute, and how it will be coming. Now if we take a is equals to 1, b is equals to 1, here both will be 1 1 1 bar plus 1 bar 0 plus, here only c term will be there, here 1 plus a 1 plus a, so it will be very easy to substitute. So using BCB constraint, if it assume any value, it will be very easy. So we will be taking a is equals to 1, b is equals to 1. For a fixed value, we can deduce the total function to a very simple manner by taking a is equals to 1, and this is the Boolean constraint propagation method. And we have given some BDDs and sat both differences and what will be there, everything we have given in a way. And coming to the two level logic gates, as already we know a K map, where we have serial and digital logic design, same process will be taken here. In the basic idea, we have to get a good answer, try to get a good answer than the best answer. First try for a good answer. Let us take an example like this, and we have using a K map, all we know that K map, how to read and write K map, as they have circled these four ones as one unit, and this is one of the best method. And other ways we can circle like this also, and this is also correct, but this is not accurate, but it is a good method. This is one of the way we can get. And the other these ways are this is also a best method, and this is not that good. Try to get at least a good method by using K-map. As everyone know K-map, by taking a variables like here and here 0 0 1, and for this a b and c d value where it will get 1, we will be marking here, and using K-map rules we will be mapping everything. And we have seen here, and we will be comparing these best and good solutions, and which will be more easy, and less number of K-maps we have used everything. In the coming slides we will be knowing don't gates where we are using, and what will be this and everything. And now here I have got you some important topic called cubes of a prime cube are like that, etc. Now let us take this example where a b c d, the star may be any values 1 or 0. For these values we will be getting output as 1. This is one of the cube level p. So this is one cube, this is one cube, this is one cube, these are everything cube level. As we are indicating these as cube levels, which will be important, we will be coming to know in the next slides. And they have given a perfect K map with minimum number of mappings, how we have to reduce and expand and find the minimum base, as already we know, we have seen in DLD. Those are everything rules where we will use it. And there are three methods mainly for every designing a pod. We have to mainly simplify the big given expression, and then remove what are unnecessary to us, and add if we need anything in our circuit. Coming to the simplifying the node, let us take an example a plus ab plus bc. In this node we can simplify when we take a common, a into 1 plus b plus bc. 1 plus b is nothing but 1. So we can write a plus a plus bc. This is a simplifying node. And removing a node, let us take this example. And now I have this z is equals to ab, I have removed it because in the place of z I have substituted ab. This is enough. So this node is not equal, not important to us. So this is removing a node method. And now I am doing adding new nodes. How to add new node? Let us take this example. In x y z there are 16 letters a b 1 2 3 4 5 6 7 8 9 10 11 12 13 16. These 16 literals are there. Now the common point in this is ab plus c, ab plus c, ab plus c. Now that I have differentiated from them and written here. This is the divisor, and this q I will be using here. Now when we count these devices 1 2 3 4 5 6 7 8 9 10, literals are less, and another node is added, which is very important and easy to know. This is adding method, and every function can be written as divisor into quotient plus remainder. As if we take f is equals to ac plus bt like this, a plus b is simplified like this. This is a divider remainder. It can, you writing this like this function is very easy to understand. They have divided like this, divisor, quotient and remainder. And this kernel and co-kernels of a function is very important to know. I will be explaining this kernel and co-kernel in a easy manner. Yeah, this is the kernel example, detailed way what is kernel and what is co-kernel, where we are using this. I'll be explaining here. With this algorithm, overall recursion tree looks like this. F is equals to AC plus BCE plus DE plus G. AC plus like this we have given. Now let us take this. This is nowhere cubes, nowhere cubes, cube. Coming first of all, we will discuss these cubes. Here when we see both in this both ABC, ACE, BCE, and here we can take common CE. When we take CE as common, we will be getting A plus B as the sum. The sum is known as kernel, and which we are taking common is known as co-kernel. Like this we will be taking, and from which two terms we will be taking, those are cubes. Like this, this is the cube. And if we take an example in the A, C, E, B, C, E, and D, E, we can take a common letter E. This is when we take here we are taking a common letter. This is co-kernel, and this is a kernel. What are all the things we have got after taking common? These three terms we will be calling as cubes, and this single term G, like A, B, A plus B, these terms are cube free terms, because these are cubes. AC, it is combined term, it is multiplied, so these are cubes, and cube free terms are G here. If it is B, then B. And with the help, and now here if we take A will be not useful in taking common or anything reducing, so nowhere. B is also same like that, nowhere. Like this kernel and co-kernel we are using, and the method will be going recursively, and finally we will be getting a final SOP product, which is very easy in solving the Boolean expression with the help of kernel and co-kernel. So co-kernel and kernel is useful to us in solving problems. As I already said you, cube free, which terms the terms which doesn't have product terms like A plus B plus C, or simply A, like that products. And coming to the single cube devices, as we know, single cube devices play a role where to save the literals and minimize the literals. We will be using this concept. Let us take an example P, Q, R, A plus B, and these are the terms, and we will be taking a map like this A, B, C, D, C, and everything, and we'll be notating variables like 1, 2, 3, like this. And when A, B, C is there, here we will be taking 1, 1, 1. Here also there will be 1, 1, 1, and A, B, F, G, A, B, F, G. That A, B, D values, A, B, D values, E, G values, and under A is equals to 1, B is equals to 1, and T is equal, like this. We'll be taking all the values and substituting here, and this is the clear picture of the topic what we'll be discussing now with the help of kernel and co-kernel. And we have to map wherever in the columns 1 continuously is not required. If there is a gap also, it is okay. Look at here, there is a gap, here there is a gap. If the gap in the columns is okay, then we can map it. Now we will be mapping this, and in the B value will be mapping like this. So like that we will be mapping A and B, and here we have given like row wise. Now we will be taking a row wise, as we have given we have to get a common things row wise and column wise, and we have to get a maximum rectangle. This is the maximum column, this is the maximum column. And now when we will be mapping with the rows like this and like this and like this, this is the common cube in the rectangle, this is the common cube in the rectangle. And we have a formula to find the common cube in the rectangle. L is equals to E minus 1 into sum of rows into weight of R minus C. And now I will explain you one of the example. L is equals to C minus 1 into now let us take this example ABC plus ABD plus EG in the row wise. In this example, C means column, and here there are two columns, these two, C value should be 2, and in C minus 1, 2 minus 1, 1. And in this row summation of rows into weight, and weight means each term how many times it is repeating, like that we have to take it. And there are three terms, 2 minus 1 into 3, 3 minus again column is 2 and 1, so we will be saving 1 literal here. And detailed expression is given here on how we have to solve it, and with a clear way, co-kernel, kernel and everything is given, which I have explained you now. This is the process, and how we have to map, and which is the maximum rectangle, everything. Now we will be coming to don't care functions. Don't care is very important in solving. This is a peculiar topic, one of the peculiar topic using don't care to simplify digital design. Let us take this example: x is equals to ab and f is equals to abc. These are the primary inputs, and this is the primary output. Primary inputs are a b, and this input is taken here, and for this f value it is important. So let us take an example: a b x. Does it occur? What values of a and b? X is 0. If we keep a b as 0, here multiply a dot b. If both are 0, x is 0. Yes, it occurs. If both are 0, x is equal to 1. No. Like that we will be seeing every value. For x, b, y also we will be taking care like that, and we will be observing like this. There is no, for x here we have a into b. For y we are not having any simplified function, so we will be getting these two particular topics. We are not getting the output, because if b is equals to 0, if we keep b is equal to 0, then x is compulsory 0, but we are getting 1, here also 1, so these two are not possible. Remaining everything is possible. Now we are here taking a k map for y and xb for f is equals to 1. So, what are all the possible outcomes? We will be substituting here, if it these values x, b, y values, and f is equals to 1. For which value f is equals to 1, we will be substituting here. And the don't cares are two functions. These two don't cares will be substituting here, and don't cares are also useful in k maps, which will be taking as 1, and we can map that. We can map that also to find the simplified expression. The simplified expression is f plus yb. Okay. And if you take another example, does f affect z? This is the question. F affect z. Now let us take an example: f x d. F x d is the z function, and we will be changing f value. If it is 0, 1. If it is 0, it is 1. 0, 1. And substitute, if now substitute here 0, 0, 0, then find z, and 1, 0, 0, what is z? And substituting like that, we will be getting here for this condition we will get z is equals to, for any condition now we are getting z is equals to f, except for this condition. Remaining all condition it is not affecting z. So we are given a k map, and which value is d and everything. And for this k map we are using this solution, which will be understanding easily by looking into it. And there are don't care three types: satisfiability, don't care, and controllability, observability. Satisfied means belonging to voice inside the Boolean logic network. These are the voice inside the logic network, so we will be seeing in a detailed manner. Yeah. This is a satisfiability don't care. These are the inside Boolean wires, which we have said in the definition. Let us take this example, and this wire satisfiability don't care x of ab for impossible patterns of xab, and this is the expression. The output expression of satisfiability don't care is x into XOR of expression of x. This is the function. Let us take this example: x into, we will be taking XOR gate for this, and we will be getting finding the final expression. So this expression will be the don't care function of this function, and we will be finding the final output of this satisfiability don't cares. And coming to the controllability don't care, there are some rules we have to use and implement in this function. Let controllability, what we have seen, we will go through it. Controllability: patterns that cannot affect at the inputs of a network node. What are all the nodes which will be not affecting the input? We are going to see now. These are the input gates a b c d. This will be not affecting. Just example, this controllability don't care is equals to for all variables not input of f. Now we will be taking here which values are implemented. C is there, D is there, A is there, D is there. So not implemented value is B. So we will be taking here B, and into sum of inputs of SDC. Sum of inputs of SDC means we will be taking, as we already know the formula, x into XOR of inputs of SDC. So we will be applying here for all of B, as I already told B, and the input x into XOR of that and y into XOR of that, and we will be getting the final simplified expression. This is the controllability don't care function. And the final one which we are going to discuss is observability don't cares. Patterns that mask a node's output at network's output. This is the function we have given here. Let us take a patterns a, b and c. Makes this a, b makes z insensitive to f's value. With the help of a, b we can make f is not related to z like that, only ab is enough. This will be saying in observability don't care, and where we have given the some conditions like this, not get observed is equals to 1. This condition should be satisfied, and it is where the output z is insensitive to f, which I already told. These are the sum of the don't care functions and satisfiability and everything which I have explained now. Single cube devices which helped me to learn some of the basics to VLSI CAD. This is a part 1 which I have done in 5 weeks, so that which will be helpful to designing easily with the help of this to solve a complex problem into very simple manner. And the main outcomes of this project is nowadays everywhere, if you take a mobile chip is there, will be in that chip complex devices will be stored in a very complex manner. Applications is stored in a very simple manner with the help of VLSI CAD. Everywhere we will be using this VLSI CAD is very important in a nowadays in designing everything, mobile phones, laptops, chips, etc., microcontrollers, etc., everywhere. So my I'm still learning VLSI CAD. There are many part 1, part 2, part 3 under the Coursera. I will be learning in the future sessions. This is one of this is only part 1 which I have learned some basic concepts which will be used to solve large scale integrated circuits. So thank you.